Hey there, we're going to continue our related rates study. So this is video 4 of the series. And the example we're going to explore is this one. So a particle moves along the graph of y equals x cubed in the first quadrant so that its x coordinate increases at a rate of 5 centimeters per second. And then the first question is, how fast is the angle of inclination of the line joining the particle to the origin changing when x is 2 centimeters? All right, so here's our first question. Remember, with word problems, always focus on the task. What is it that you're supposed to do, or what is the question? So here, how fast is the angle? So we're looking for a d theta of something. And because things are changing in terms of per seconds with respect to time, that means we're looking for d theta dt. So how fast is the angle of inclination of the line joining the particle to the origin? So let's dissect that. The origin is the point 0, 0. So we have the particles moving along y equals x cubed. So we want to find the angle of inclination of the line joining the particle to the origin, and then the rate of change of that when x is 2 centimeters. Part B, how fast is the y coordinate increasing when x is 2 centimeters? So there are two things going on here. So what picture are we going to draw, right? The first step in our related rates problem is draw a picture with variables and then identify your d what. So let's see what is happening here. So we have a particle moving along y equals x cubed in the first quadrant only, and then as that particle moves, there's a line segment joining that particle to the point 0, 0. So let's take a look at that. So essentially there's the particle, and then the line segment that joins the particle, the little green dot, let's call that the particle, and then as it moves along y equals x cubed, that purple line or blue line is the line segment joining the origin to the particle. So as that particle is moving, notice that then that line segment moves as well. So it goes from being really small at 0, 0 to it gets larger. And so let's find the angle of inclination of that. All right, so bringing that picture in and completing a triangle in here, we have this as a right triangle, and so we have our point here is the point xy, but y is given by x cubed, so I can call it x comma y equals x cubed, so x cubed. So that is our point. So where is the angle of inclination? So the angle of inclination is right here, right to the point. So there's the line segment joining 0, 0 and the particle. So the angle of inclination is the angle between that line segment and the horizontal, which is the x-axis. So that is our angle of inclination, not to be confused with just that in between the curve and the segment is the whole thing. So theta is, let me make it bigger, the whole thing. All right, so then in our triangle, this is x and this over here is y. So we already kind of wrote the point first. So y is x cubed, which gives us then that point. All right, so how fast is the angle of inclination of the line joining the particle to the origin changing when x is 2 centimeters? So here is our picture with variables. We have theta, x, and y. Those are the things that are changing. I guess technically this is also changing, so you can call it something else, w. So let's see. Identify our d what. So what do we have? So we have that in the first quadrant, so that is x coordinate increases at a rate of 5 centimeters per second. So the x coordinate increases at a rate of 5 centimeters per second. So that means that we have dx dt is 5 centimeters per second. And in part A, how fast is the angle of inclination of the line changing? So I want d theta dt when x is 2 centimeters. And so we have a picture with variables, and now we have our d what. So the next step is come up with an equation that relates the variables in the numerators of our d what. So what relates x and theta in this right triangle. Now I am going to get rid of w, the hypotenuse, because we don't really have anything in here that mentions the hypotenuse at all. So I don't want to leave it there and create confusion. Whereas I do know that y is equal to x cubed because this particle is moving along that curve. So I know that y is equals to x cubed. So let's use that. So I know then that y is equal to x cubed. I have x and I have theta. So opposite, adjacent, and theta, that will mean tangent. So let's write that down. So that means that tangent of theta, which is equal to opposite over adjacent, would be tangent of theta is opposite, so y over adjacent, which is x. But we know that y is equal to x cubed. So make that substitution. So I'm going to have x cubed over x, which is x squared. So my equation then is tangent of theta is equal to x squared. So that is my formula that relates the variables in the numerators of my d what's, right? I have theta and I have x. So I want my formula to just have thetas and x's. So here when I had theta, y, and x, that's not okay because I don't know anything about y, except that y is equal to x cubed, but now I can change it to just thetas and x's. So now we take the derivative with respect to the variable in the denominator. So take the derivative with respect to t of both sides. So when we do that, what are we going to have? So I'm going to have the derivative with respect to t of tangent theta equals the derivative with respect to t of x squared. Now things are changing with respect to time, so that means theta and x are both functions of time. So when I take the derivative here, I have to use the chain rule, right? Theta is really theta of t, x is really x of t. So we need the chain rule when we take the derivative. So the derivative of tangent is secant square of the inside left alone times the derivative of the inside, so the derivative of theta with respect to t. So d theta dt equals the derivative of x squared. So 2 times x, but then x is really x of t, so times the derivative of x with respect to t. So dx dt. And now we can put in what we know. What do we have? So we have dx dt, which is 5 centimeters per second. We don't know d theta dt, but we want to know d theta dt when x is 2 centimeters. So we're going to put that in now. Which notice that we're going to need something for secant square of theta. So let me write that as secant theta square, because that's what that means, times d theta dt equals 2. We want to know when x is 2 centimeters and when dx dt was 5 centimeters per second. So what do I put in for secant square theta? Well, let's go back to our triangle. Well, let me redraw the triangle. So we had our theta was here, this was x, which now we know x is 2, and y is x cubed, right? So that will be 8. And we're looking for secant of theta. Secant is, what is secant? Cosine is adjacent over hypotenuse, so that means that secant theta is hypotenuse over adjacent. So that means that we want to know the hypotenuse when this is 2 and that's 8. We already know the adjacent is 2. So let's find the hypotenuse. So that will mean 2 squared plus, so leg square plus leg square equals the hypotenuse square. So let's call it C. So what's that? 4 plus 64, so 68 equals c squared. So c is the square root of 68. So hypotenuse over adjacent, so that will be the square root of 68 over 2. Careful not to say, oh, let's divide that, 68 divided by 2. No, this is inside the square root and that is not. So we can put that now in here. Right, secant square theta, so it's going to be the square root of 68 over 2 square times d theta dt equals, what's that, 4 times 5, so 20. And here the 68, right, the square root of 68 squared is just 68 over 4 d theta dt. And now we can solve for d theta dt. So d theta dt, so let's reduce that 68 over 4 to 17. And so now we're going to have d theta dt is 20 divided by 17. There's a number of ways you could have gone here, right? Like, I know some of you are like, why are you leaving it as secant? I could have changed this, right? This is 1 over, secant is 1 over cosine, so I could have then multiplied both sides by cosine square, and I will have 2x cosine squared theta dx dt, and everything will already be on this side, and that's okay. I just decided to keep it this way, but you could have said this is 1 over cosine square and then multiply both sides by cosine, and now you will have the cosine square over here instead of a secant square on the left. Either way, we should still come up with the same result. That d theta dt then is 20 over 17, and our units will be radians per second. And because 17 is prime, we can't reduce that anymore other than changing it to a decimal. I prefer fraction answers, they're more exact, but if in the homework you're asked to round to a certain number of decimals, just pay attention to what decimal number you're supposed to round, but you can just leave it like that. Alright, so let's go on to part 2, or part B. What was part B asking you to do? So we're still looking at this problem. So a particle moves along the graph of y equals x cubed in the first quadrant, so that its x coordinate increases at a rate of 5 centimeters per second. Alright, we got that. Part B, how fast is the y coordinate increasing when x is 2 centimeters? So part A was asking us about the angle of inclination. Now we're saying, okay, if the x coordinate is changing at 5 centimeters per second, how fast is the y coordinate changing? So let's set up. So our setup is going to be pretty similar. So let's adjust our halves and ones. So we still have dx dt, but now we're going to want d theta dt. So let me copy the same picture and then let's rewrite what we have and what we want. Okay, so we still have the same dx dt, right? So we're going to say we have the rate of change of x. So we know that dx dt is 5 centimeters per second. So the x coordinate is increasing at a rate of 5 centimeters per second. And now what we want to know is how fast is the y coordinate increasing. So we want to know dy dt. When at the same spot, when x is 2 centimeters, which probably makes me think that we're going to need part A in this. So let's see, so we have our picture with variables. We've identified our dwats. So that's the step 2. Step 3 is come up with a formula or equation that relates the variables in the numerators of your dwats. So x and y. So I have x and y. I don't necessarily want to involve the hypotenuse again because I don't know anything about the hypotenuse. From part A, I do know theta, so we're just going to use the same expression from before. That I know that tangent of theta is equal to y over x. But now, the thing that's going to be different about this is that I am not going to change y into x cubed as I had before. Because here, I want my formula to be in terms of x and y. So I actually have a bit of a problem here because I have theta and we can't really get rid of theta, but we're going to deal with this because we have information from it from part A. from part A, we know d theta dt. What was it? We found it to be 20 over 17 radians per second. So we're going to keep this because I already know from part A the rate of change of theta with respect to t. If I didn't know that, I will need to find a way to get rid of the theta. So let's take the derivative again with respect to t. Now, notice that here, right, everything is a function of t. So I have theta is theta of t, y is y of t, and x is x of t. Everything is a function of time. So when I take the derivative, what do I need to do? Here, when I take the derivative of this, I have a function of t divided by a function of t. What rule do we need? Right, I'm going to need the quotient rule here. So that's new. Well, not new, but new in that related rates problem. So take the derivative with respect to t. So on the left side, we're going to have secant square of theta times by chain rule d theta dt, which we already know from part A, equals, and now here I need the quotient rule when I have y over x, right, because they are functions of t. So quotient rule is low, so x, d high, so dy dt, minus, so the bottom derivative of the top minus the top times the derivative of the bottom, dy dx dt, all over the bottom square. So, and that's the reason we're using the quotient rule here, is because both y and x are functions of t. So let's, and again, I didn't change my y into y equals x cubed because I want to get my hands on dy dt. That's what we're trying to find. So if I replace y with x cubed like I did before, I won't have a y in here and I won't be able to find what I'm looking for. We want the rate of change of y. And so now we can try to simplify this, or we can plug in our information. So when x equals 2 centimeters, what do we know? We know that dx dt is 5 centimeters per second, and we also know d theta dt was, what was it, 20 over 17 radians per second. And we also knew secant squared theta, right? We knew that secant, we found it in part A. So secant was the square root of 68 over 2. So secant square was actually 68 over 4, which was 17. So we can also say that we know that. And secant of theta square was 17. So this was all, these two things were from part A. Okay, so let's put all that in. So putting it all together, we're going to have secant square, which I know from part A, that's 17, times d theta dt, which also from part 8 we know is 20 over 17, equals x, that was given to us as 2. Well, we want to find things when x is 2. dy dt, that's the thing that we're looking for, minus y. When x is 2, y is x cubed, right? So then that will be 8, and dx dt is given to us as 5 centimeters per second, all over x squared, so 2 squared, which is 4. So here our 17s can cancel off, and we're left with 20 equals 2 dy dt minus 40 over 4. So multiply both sides by 4, so I'm going to have 80 equals 2 dy dt minus 40. So add 40 to both sides, so 120 equals 2 dy dt. So divide both sides by 2, so 60 is dy dt. And let's see, what are our units going to be? X and Y are both measured in centimeters, so this is going to be 60 centimeters per second is our dy dt. So that's how fast the y coordinate is changing in this particular scenario. When you have a particle moving along y equals x cubed and x is changing at a rate of 5 centimeters per second, the y coordinate is changing, then we just found it to be 60 centimeters per second. I hope I didn't make any small algebra mistakes here, but that seems to be consistent with my my notes. So this was a slightly different example, right? Notice that we needed the quotient rule in here. And so because things are changing with respect to time as third variable, or fourth in this case, that's not even included in the equations. We're doing everything implicitly here. All right, contact me if you have any questions.